Let us solve some of the numerical problems on Solow model. The question is, given aggregate production function for an economy is, that is y is equal to a times k to the power alpha times l to the power 1 minus alpha. A denotes the state of technology, k and l are the units of capital and labor in the economy. Suppose the value of a is 20, alpha is 1 upon 2, savings rate is 1/4, and population growth rate, which is denoted by n, is equal to 1 upon 10, that means 10%. We have to find out the steady state level of output per worker first, then the rate of growth of aggregate output in steady state. Third question is to find out the golden rule value of capital per worker, and last question is to find out the golden rule value of consumption per. Okay, let's solve it one by one. Okay, so let's write it in this fashion, that is y is equal to, y is a function of labor and capital, which is equal to the value of a is being given us as 20, k, capital K raised power alpha is 1 upon 2, we can write it as 0.5, and L is also 1 minus alpha, that means 1 minus 0.5, it is again 0.5. So first thing is, we write this aggregate production function in intensive form. By intensive form, what we mean, we write it in per worker form. That means we divide by L, okay, each variable. So here we have L, here we have also L, okay. So it becomes, so it will become like this, okay. And let's denote K upon L as small k, okay. Capital labor ratio is equal to K. So this function can be written as Y. So here we also divide by L. So this denotes output per worker is equal to F of, so L upon L is 1, so K upon L is small k. Output, that means capital per worker, is equal to 20 small k raised power 0.5, okay. So we have written the given production function in per worker form, that is in intensive form. Now the first question tells us, find the steady state level of output per worker, okay. By steady state, what we mean, at steady state capital per worker is not changing, okay. So I explained all this stuff in the introductory part of the Solow model. You can check out that very video, okay. So at steady state, let me write it here. At steady state, okay, capital per worker does not change at all. That means change in capital stock in the economy is equal to 0, okay. Now what is change in capital stock? Change in capital stock is simply equal to S times F of K, that means savings, rather savings is equal to investment in, you know, Solow model, minus NK. N means the population growth rate times K, that is capital per worker. It should be equal to 0, okay. As we have learned in the earlier video, at a steady state, okay, that means in steady state capital per worker is constant, that means change in capital stock is equal to 0. And let's show it graphically to make it more sense what exactly we are doing here. So we have here a capital per worker or capital labor ratio. On this vertical axis we have output per worker and other stuff, okay. So given this is our F of K, okay, this NK denotes the population growth rate, and let us denote it by, okay, this is our NK, and this shows our investment. We know that in Solow model, savings is actually equal to investment. So let's draw it like this. So this is our S, FK. So at steady state, at this point you can see savings is exactly equal to NK, or we can also say that this NK, by this NK, it is a kind of like depreciation. Population growth is one reason why capital stock per worker shrinks. Okay, and you can think, if this is the investment, okay, we know that capital stock does not change at steady state. Okay, any increase in investment is used to equip new workers with capital as population grows. So our change in capital stock will be equal to 0. Okay, the capital accumulation, this NK denotes the capital accumulation required to keep the K constant as population grows. Okay, so that's why we have SFK minus NK is equal to 0. I have explained it in the earlier video. I am not able to explain all this stuff here. Okay, so this function should hold this relationship. Now what is our SFK? This is our FK. Okay, so our FK function is, that means FK in intensive form, it is 20 raised power 0, sorry, it is 20 k to the power 0 0.5 k to the power 0 0.5. Now SFK means savings rate is being given us here 1 upon 4, so we can write 1 upon 4 times 20 k to the power 0 0.5. So SFK becomes 5, 4 ones are 4 5s are, so 5 k to the power 0 0.5. So in this place I can write 5 k to the power 0 0.5 minus population growth rate is 1 upon 10. 1 upon 10 k should be equal to 0. At this point you can see our savings are exactly equal to this NK. Solving for k here, so we can write it in this fashion. Okay, so let me write it here. 5 k to the power 0 0.5 is equal to, transposing it will become 1 upon 10 k, transposing this k here, so we have transposing this 10 here, it will get multiplied, so 5 tens are 50 will be equal to k divided by k to the power 0 0.5, and this can be written as 50 is equal to, transposing this here, it will get subtracted with this exponent, so we have 1 minus 0 0.5 in the numerator. If I transpose this term, it will get multiplied and its exponent sign will change. That is why I am writing it in this fashion. So our 50 will be equal to k to the power 0 0.5, and we know, okay, when I write it, it will become k to the power 0 0.5 is equal to 50, which implies our k will be equal to, if I transpose this 0.5, it will become square here, so it is 50 square, which gives us, and let me rub this out here, so k will be equal to 50 into 50 is 25, k will be equal to 25, 50 into 50 is 25, is it 2500. Okay, so this is our steady state capital per worker, but we need to find out the steady state output per worker. Okay, so this is our steady state, and this is our output per worker function. Okay, we plug the value of steady state capital per worker in this equation to get output per worker. That means f k star will be equal to 20, so k star is 2500, so in place of k I can write 2500.5 means under root 5 here, so this comes out to be 2500, so this comes out to be 20 into 50 it comes out to be 1000. That means our steady state output per worker will be 1000. Second question is the rate of growth of aggregate output in the steady state. Okay, we know that, and here you can see graphically that in the steady state capital per worker is constant. Okay, so output per worker is constant, thus the growth rate of steady state output per worker is here 0. That means our aggregate output will be constant. That means the growth rate of aggregate output will be equal to 0 here. Our aggregate output at steady state will show 0% of growth, because any capital that is being invested is used to equip new workers with capital as population grows, because we don't have here depreciation. So this is for second question. The third question is to find out the golden rule value of capital per worker. Okay, so third is to find out the golden rule level of per worker, golden rule level of capital per worker. Now the steady state value of capital that maximizes consumption per worker is called golden rule value of capital. Let me repeat it here. The steady state value of capital per worker that maximizes the consumption per worker is called the golden rule value of capital. I will not write it here. Now, what is consumption? Output per worker will be equal to, consumption per worker plus investment per worker. We know it. Solving for consumption, that means consumption per worker at steady state will be equal to output per worker minus investment per worker. Okay, here since we don't have differentiation, we can write it in this fashion. C will be equal to y is our fk steady state capital per worker. In place of investment we have nk. Okay, so investment will be equal to population growth rate times capital per worker here. So our consumption function will be like this. That means our steady state consumption per worker will be equal to f of k star minus nk. Okay, the steady state value of capital that maximizes consumption per worker is called the golden value of capital. That means we want to maximize consumption. Okay, our endeavor is to maximize consumption. So this is the maximization problem. Okay, we know that the first order condition for maximization requires that the change in consumption per worker at steady state level with respect to change in capital per worker at steady state level should be equal to 0. That means we take the derivative of this function with respect to capital. So derivative of f k star will be f dash k star, okay, k star minus derivative of k star is 1, so we are left with n. It should be equal to 0. Okay, so this is our fk. What is our f star k? Sorry, f dash k means the derivative of this production function with respect to capital. So we have the exponent becomes coefficient 0.5 into 20 is 10. We will get k to the power negative 0.5. This is our f dash k. So in place of f dash k I can write 10 k to the power negative 0.5 minus n. The population growth rate is being given us as 110. So I can write 110 10 10 10. It should be equal to 0. Okay, so that gives us 10. Transposing it to the numerator, it will become positive 0.5. The exponent should be equal to 10, 1 upon 10. Reciprocating both sides or multiplying, cross multiplying, so we will get k to the power 0.5 is equal to 10 tens are 100. That gives us k will be equal to 100. Transposing exponent, it will become exponent but reciprocated. That means k will be equal to 1s, 10s, 100,000, 10,000. That gives us the steady state, rather the golden rule value of capital per worker. Okay, here one thing is important. The condition for golden rule level of capital per worker is simple. It is the condition, since we have taken the derivative of this, you know, function, this function with respect to k, this is our output, that means capital per worker. Okay, when we take its derivative, that means here what we have done, this equation tells us, and let me write it here, we have got f dash k is equal to, if I write it here, is equal to n. That means at golden rule level of capital per worker, f dash k means marginal product of capital should be equal to, n is our population growth rate. Okay, so it should be equal to the population growth rate. This is the condition for golden rule level of capital per worker. That means when the slope of the production function, that means this production function and the slope of this nk, function, this curve is same, this red line, it is red, that slope will be constant at all points. When, let us say here it occurs when the slope of, so this gap denotes our consumption. Okay, when the gap between this production function and this nk line is greatest, we say corresponding to this gap, we have our golden, let us denote it by k star g. So this is our k star g, golden value of capital per worker, means when the difference between the distance between the production function, that is out in intensive form, the difference between production function and this depreciation function or population function here. Okay, when the gap is highest, at that point we have the what we call the golden rule of capital per worker. Okay, third tells us find out the corresponding golden rule value of consumption per worker. So fourth, consumption per worker, since we got the relation between consumption per worker is this, rather this very thing. So our consumption per worker will be equal to f k. So at golden rule value we got k is equal to 10,000. So we can write in this fashion, sorry, let me see what we have to do here. So uh, fk is actually, so let me write it here, c will be equal to fk. So fk is this function, so we have 20, and corresponding to this golden value of capital per worker we have 10,000. So we write here 10,000 raised power 0.5 minus, we subtract nk, n is population growth, it's not getting its space here, so let me, if some space is being left out, okay, so let me write it here. So golden rule value of consumption per worker will be equal to fk. So this is our fk, in place of k we have this golden rule value of capital, that is 10,000 raised power 0.5 minus population growth rate is 10 times k again is 10,000. Solving this, so we have 10,000 raised power under root 10,000 is 100, so this becomes 20 into 100 minus 1 gets cancelled, so this is 1000, which implies golden rule value of consumption per worker will be equal to 20 into 100 is 2000 minus 1000, which comes out to be 1000. Okay, so I hope I make myself clear. Thank you.